In this video, we'll be using the Hunter-Nash graphical method for a liquid-liquid system.
The Hunter-Nash method employs four assumptions. First, the two components are considered to have equal and constant heats of vaporization. Additionally, changes in enthalpy, heat of mixing, and heat losses from the column are negligible. Lastly, the column pressure is uniform, or in other words, there is no pressure drop. These assumptions lead to the condition of constant molar overflow. This means that the liquid and vapor rates in the rectifying and stripping sections are constant, but not necessarily equivalent. Now, onto the problem. 500 kg per hour of 40 weight % DPH indocursan is to be extracted using a countercurrent system with 500 kg per hour of solvent. The solvent consists of 98 weight % furfural and 2 weight % DPH. This system will be used to produce a raffinate of 5 weight % DPH. Part A. Prepare a right triangular plot for the system and calculate the number of stages required to obtain the separation. First, we must use our given equilibrium data to plot an equilibrium curve on our graph. Then draw a curve that passes through each point. This will be your equilibrium curve. Next we must draw in the tie lines from the given information. Now that we have set up our graph, we must calculate our feed, solvent, extract, raffinate, and mixing points so that we can complete our plot. We already know the feed and solvent points for our system because they are given to us in the problem statement. Using these numbers, plot both the solvent and feed points. We also know enough information to solve for our raffinate. Using the information given to us, we can find that the raffinate is to the left, on the equilibrium line at 5 weight % composition. Now we can do a material balance to find our mixing point M. Find the composition for each species at the mixing point and graph your result. We can now use this to find D1. Your graph should look like this at this point in the problem. We can now draw a line from R through M, and wherever it touches the equilibrium curve is where our extract point is. Now we are ready to find our pinch point, P, that will allow us to start finding how many stages our system will need. Draw a line from F through E1. Draw another line from R sub N, through S. Where these two lines meet is our point P. Find and mark R sub 1 by using the tie lines from point E1. Then draw a line from R sub 1 to P, and where it intersects our curve will be point E sub 2. Repeat this process until you get to your raffinate leaving from stage N. Count the number of tie lines you drew, and that will be the total amount of stages required for this system. When we finish, we end up with a total of 6 stages. Part B. Calculate the amount of DPH in kilograms per hour, in the extract at 80 degrees Celsius. Once we have our extract species compositions, we are ready to continue with our material balance. We start by taking the material balance over the entire system. This is saying that our feed flow rate plus our solvent flow rate is equal to the raffinate at stage N plus our extract flow rate at stage 1. This is true for a countercurrent system such as ours. Next we solve the material balance with respect to DPH. We can simplify this down to 210 kg per hour is equal to 0.05 R sub N plus 0.269 E sub 1. We can then use substitution all linear combination to solve for R sub N and E sub 1. These will be equivalent to our raffinate and extract flow rates respectively. You should end up getting a value of 269.406 kg per hour for the raffinate and 730.594 kg per hour for the extract. We can now use this to solve for the amount of DPH in the extract at our given temperature. To solve for this value, we simply need to take the mass fraction of DPH in our extract and multiply it by our extract flow rate. This is equal to 730.594 kg per hour times 0.269, thus, The answer to part B or our problem is 196.530 kilograms per hour of DPH in our extract at 80 degrees Celsius.